So in this problem, using the principle of mathematical induction, we need to show that for all n belonging to the set of natural numbers, this expression is an integer. Okay, let us begin. Now first, what we'll do, we're going to consider the mathematical statement Pn. So let that statement be denoted by Pn. So we're going to name the statement as statement number 1. Now, in order to verify that the statement P of n is a true statement, we will verify whether if it is true for the first natural number 1. So let's say for n equals to 1, then we're going to get P of 1. So P of 1 statement will be 1 raised to the power of 7 divided by 7 added to 1 raised to the power of 5 over 5 added to 2 over 3 multiplied to 1 cubed minus 1 over 105. Now we have 1 over 7 added to 1 over 5 plus 2 over 3 minus 1 over 105. Now when we combine them, we're going to get a value equals to 1. Now, clearly, 1 belongs to the set of integer. So 1 belongs to the set of integer. So we can say here that the statement, this simply tells us that the statement P of n is true. So this is a true statement and it's going to be true for the first natural number 1. Now we have to verify that it is true for the other natural numbers as well. So here we will suppose that we consider another integer m such that let P of m be true. So here we're considering another integer value m such that the statement P of m is a true statement. That is, in essence, we are saying that P of m such that we have m raised to the power of 7 over 7 added to m raised to the power of 5 divided by 5 added to 2 over 3 times m cubed minus m over 105. So here we're saying that this particular statement is a true statement. That means the expression must be an integer. Fine. So we will consider this to be statement number 2. And using this statement, we'll need to verify that the statement P of m plus 1 is true. P of m plus 1, where m plus 1 is the integer that is consecutive to that of m. And what is P of m plus 1? The statement P of m plus 1, that is essentially given by, all we have to do is replace the m value with m plus 1. We have m plus 1 whole raised to the power of 7 over 7 added to m plus 1 whole raised to the power of 5 divided by 5 added to 2 over 3 multiplied to m plus 1 whole cubed minus m plus 1 whole divided by 105. So we have to show that this expression is an integer. That is our goal, to show that this is an integer as well. Fine. So let's label this as statement number 3. Now how do we verify that this particular expression is an integer? So here we'll be taking the help of statement number 2. So here from statement number 2, we have already considered that the expression is an integer, this expression. And since it is an integer, so what we can do, we can suppose that m raised to the power of 7 whole divided by 7 added to m raised to the power of 5 whole divided by 5 plus 2 over 3 multiplied to m raised to the power of 3 minus m over 105. Since this is an integer, we can express the entire expression in terms of lambda, where lambda is just another integer. Fine. Now we will be using this to verify the statement P of m plus 1. So now what we'll do, we'll take the expression m plus 1 whole raised to the power of 7 over 7 added to m plus 1 whole raised to the power of 5 divided by 5 added to 2 over 3 multiplied to m plus 1 whole cubed minus m plus 1 whole divided by 105. So here we will need to expand each of the expressions. So I'm going to specify the expanded form of each of the terms to get. Now what we'll do in the next step, we're going to take the first term of each of the expanded expression. So from the first term, we'll have m raised to the power of 7 over 7. Okay, so let's write that down. we'll have m raised to the power of 7 divided by 7. Then we'll take the next first term from the second expansion of m plus 1 raised to the power of 5 over 5. We'll have m raised to the power of 5 whole divided by 5 added to. Now we'll take the first term of the third expansion, so that's going to be 2 third multiplied to m cube. And then we take the first term of the last expansion, which is negative m over 105. So this is going to be one single term. Fine. Then what we are going to multiply 1 over 7 with each of the terms of the first expansion, excluding the first term. So that's going to leave us with m raised to the power of 6 added to 3 times m raised to the power of 5 plus we have 5 times m raised to the power of 4 plus 5 times m cubed added to we have 3 times m squared plus m plus we have 1 over 7. Okay, then we have we're going to multiply this 1 over 5 to the remaining terms of the second expansion. That's going to give us m raised to the power of 4 plus 2 times m cubed added to 2 times m squared plus m added to 1 over 5. Next, we have 2 over 3 multiplied to the 3 terms. That gives us 2m squared added to, we have 2 times m added to 2 over 3. And then we have the last term, which is negative 1 over 105. Now, this particular expression is nothing but lambda. We have already considered that to be equals to lambda. So that means we now have lambda added to all of these terms. So here what we'll do, let's do one thing. Let's combine 1 over 7. Then we have 1 over 5 added to 2 over 3 minus 1 over 105. So this is going to be one combined term, and to it we're going to add the remaining terms. That is going to be m raised to the power of 6 added to. Now we have 3 times m raised to the power of 5 added to. So 5 times m raised to the power of 4 added to m raised to the power of 4. So that's 6 times m raised to the power of 4. Then we have 5m cubed and then 2m cubed. So that's going to be 7m cubed. 7m cubed added to 3m squared plus 2m squared makes it 5m squared. 5m squared plus 2m squared. So that's 7m squared. Next we have m added to m and then 2m. So that's going to be positive 4m. Right. So here we have an integer lambda. So when we combine these fractions, we're going to get 1. And then we have the remaining terms, which is m raised to the power of 6 plus 3 times m raised to the power of 5 plus 6 times m raised to the power of 4 plus 7m cubed plus 7m squared plus 4m. Now we have already considered lambda to be an integer. M in this case is a natural number. Now that means that when we take the sum of all of this term, that's going to give us some integer, which we can denote in terms of beta. So that means we have showed here that this entire expression is an integer, which proves the statement p of m plus 1. So that means we can now say this simply tells us that the statement p of m plus 1 is true. Hence, we can generalize and finally say that the original statement p of n, this is going to be a true statement and is going to be true for all values of n belonging to the set of natural numbers. So that means any natural number that we pick up, the statement p of n is always going to be a true statement. Hence proved.